thing that we're going to talk about in statics is just vectors. And so the way that we're going to basically think about vectors is they're simply directed line segments. So if I have a point A and a point B, then a vector is basically just a line that we walk along. So we say that we can go from point A to point B, and we have a length, right? There's a distance between point A and point B, right? So that distance is equal to point B minus point A. And then we also know that this has an arrowhead telling us that we're going to walk from here to here. So vectors are simply these just mathematical things that we will use and turn out to have a lot of use in statics and mechanics in general, because they provide us a critical concept of length or magnitude, size, and direction. So sense, going from like A to B. All right. But one of the two critical particular things of vectors is they combine with a very specific rule. And when we say combine, we mean vector addition. And then they also transform from one coordinate frame to another coordinate frame. That last one will become a little less, isn't so important in statics, it's more important in dynamics, but we'll touch upon it a little bit as we go through the class. All right, so let's think about vector addition. So let's say we've got a table. So here's a little table, and I am going to go ahead and do the same thing that I did over here. I'm going to walk from one corner of the table, whoops, to the other corner of the table. So I'm going to walk from this point all the way over to this point right here. And so this is going from point A to point B. So if I'm standing on the table and walking, it looks like I'm walking in a straight line, and everything looks good. Let's say somebody decides to slide that table. So we'll create another table. Oops, maybe. So there's our other table, and so let's say this thing slides downward like this. And so what happens there, right, is I don't end up, if I think about in terms of sort of the sort of if we were to consider sticking a reference frame here, right, an X and a Y, then with respect to this one, I end up here if this table gets pushed from here to here, right? So if there's this line, right, then we'll call this Q, and this line P. So I'm walking from A to B, but at the same time, this is getting pushed from P to Q. And so I actually end up here at B prime. And so what happens here, right, is my total motion is a combination of the motion from A to B and then this also motion Q of the table, making my total end motion being this vector right here, which we'll call R. All right, so what we have here, right, is we have a triangle. We've gotten two vectors, a vector of me walking from A to B and a vector that represents the motion of the table from as it gets pushed downward and to the right, that combine to produce the total motion that I actually undergo with respect to some sort of reference frame or some sort of observer might be a better way to. So if somebody was standing here and watching me, I would, as I'm walking from A to B and this table is getting pushed, I would end up here rather than here. So this specific combination here is basically a graphical representation of adding a vector, right? So what I'm doing is I'm taking the motion of me walking from A to B and combining it with the motion of the table as it slides down the corner. All right, so this is called the triangle rule of vector addition, and basically it says, I'm going to get rid of this, it simply says that if I have two vectors, I put them head to tail, and their combined response forms basically a triangle, right? So if this is vector A, and this is vector B, then vector R here, the resultant, is equal to the sum of the two motions of A and B. So you can think about it as a path in space. So if I start here and I walk along this line and then walk down this line, I end up here. The same effect is R represents the net motion that I've undergone. So if I'm walking from here to here, I end up at this point, right? So what we can say right here is a graphical representation of A plus B. And this is known as the triangle rule of, oops, can't spell, of vector addition. All right. Now, we have there's some specific consequences of this, right? So if I were to, let's basically grab this and let's move it over here. Delete that, right? I'm also going to delete that. So it doesn't really matter which order I do these in, right? So if I want to say head down B first and then go up A, I'm going to still end up with the same vector as if I did the other one first, right? So if I go, so here's B and here's A and here's A and here's B. It doesn't matter which way I walk these paths, right? I end up at the same point. And so that is a statement of the commutative property of vector addition, to say that A plus B is equal to B plus A. All right, so that's convenient and that's good to know. So vectors already have a addition type property that looks a lot like regular math addition, right? Regular number addition. Okay, so we've got our vector addition concept. Now we also have well, we'd like to also introduce a negative vector. Or a subtraction, right? So if we have addition, we have subtraction, and the way that we're going to do that is we're going to think about it in terms of addition of a negative. All right, so if I have a vector p, right, the negative of vector p is the same thing but pointing backwards. So simply, if I walk from A to B here along P, the only thing that changes for negative P is the sense in which I'm going. So from here, negative P, I'm going from B to A rather than A to B. And that basically combines into subtraction by thinking of it in terms of addition of a negative, right? So if I have P plus minus P, right? So I've walked to B and then I've walked back. My net motion, of course, is going to be, will technically be some other vector, C, right? But that vector is going to be 0 because I've walked back and forth. All right. For arbitrary vectors, you just think about it in terms of A plus minus B equals some sort of resultant R. All right. So that's the way we think about negative vectors. Now, negative vectors are made up of are built in a specific way, and we think of negative vectors as the result of a scalar multiplication. All right, so scalar multiplication, a scalar is just a number, right? So a vector has length or magnitude and direction. A scalar just has magnitude. No, we don't think of a scalar as having direction, right? So a scalar multiplication is just simply if you have some sort of scalar alpha and it's multiplied by a vector, that's basically what it is. We can make a negative vector by multiplying -1 times p, and so -1 times p is just minus p. All right, so that really all there is to scalar multiplication. When we start thinking about vector components a little later, we'll come back to this scalar multiplication concept. All right. So everything we've talked about for vector addition has been single vectors, right? But multiple vectors, multiple vector addition behaves just like it does in single vector addition, right? So if we have vector 1, vector 2, vector 3, vector 4, right, we just end up with a series of head to tail sort of orientations, right? So we have A1, A2, A3, and then A4. We stick these head to tail, and we end up with a resultant vector. That's the sum or the effective sort of walking distance or effective action of all these independent vectors, right? So you can think of, if I'm walking around in space, if I walk this distance, and then I walk this distance, and then I walk this distance, and then I walk this distance, the total distance I've traveled is this vector right here. Well, the total effective, not total distance, but the total effective change in my position, right? So while I may have walked a very long distance, I've only really gone this far relative to my initial place, right? So relative to my initial starting place. All right. Awesome. So we can think of this in terms of maybe a series of triangle rules, right? So here is a triangle rule, and then there is a triangle rule, right? So A1 plus A2 represents B1, and then A3 plus A4 represents B2, and then now, right, B1 plus B2 is given to us by R. All right, and so that's all there is to it. The other thing that it tells us is that it doesn't really matter which way we come in, right? So if we want to think about rewriting this, so we do the first motion would be like A3 or A4, or let's say we want to do, again, so we want to do maybe B2 first, and then B1 first, right? B1, B2, oops. Total, again, right, that R is exactly the same. So what that tells us is that vector addition is associative. Right, so that means if we have vector P plus vector Q plus vector S, that's the same thing as writing, and we do the PQ addition first, that's the same, we will get the same result as if we do P plus then Q plus S. Right. And that just comes from the graphical sort of interpretation of vector. It doesn't matter which of these segments we choose to walk first, it just matters that we chose to walk all the segments, right? That gets us our net change in position from this point A to this point B. All right. And that's pretty much it for, bring it back just so it's up here. And that's pretty much it for vector addition. Notice the key point here, though, is that really we just have a directed line segment or an arrow that has length and length and direction, and then we can basically just stack them together end over end and do some geometry, or stack them end to end to do our actual addition. Now, a couple of critical pieces of information. Notice we end up with a lot of triangles, right? We end up with a lot of general triangles. This isn't maybe necessarily a right triangle, or anything special, right? But so to solve these sort of addition problems, right? So if we know two vectors and we want to find this third length, we're going to end up having to use some general triangle rules, right? So general triangle laws, and that is the sine rule is a useful, or one of them, and the sine rule says that the opposite angle divided by the sine of an angle alpha divided by its opposite side, all those things are equal. So we can say sine alpha divided by length A is equal to sine beta divided by length B, which is also equal to sine gamma divided by length C. And so all these are interchangeable, right? Sine alpha divided by A is equal to sine gamma divided by C. Sine beta divided by B is equal to sine alpha divided by A, and everything else. Another useful one is the cosine rule. And this one gives us, if we've got one included angle and two sides, then we can go, so length C squared is equal to A squared plus B squared minus 2 times length A times length B times cosine gamma. All right. And so this also tells us, so if we know side B and side A, and we know this angle here gamma, then we can find length C by just calculating this. All right, and so those are the tools that you use to actually analyze these general triangles that come up when we do vector addition in this way. All right, thanks.